Today, we're going to cover the impulse response. H of T. I'm going to describe what the impulse response is, and then I'll switch to something that seems at first quite different, convolution. And we'll talk about what it means by math, how to do it graphically, which is our version of intuition for convolution. And then we'll bring it around full circle by showing how it works with Laplace transforms. Quick off topic though, how to get an effective letter of recommendation. Let me show you a letter of recommendation. Take a second just to read it. Okay. How would you rate this letter of recommendation if you were evaluating letters for a scholarship, for an internship, for a graduate school, for a job position? How would you rate this particular cadet? What type of letter is this? Is this a good letter or is this the bad letter?
It's just kind of plain, sir. So
Yeah,
I would say not very specific.
Yeah, this is bad. This is really bad. This is the kind of letter that goes into the short pile. And unfortunately, about 95% of all letters of recommendation look like this. That's why letters of recommendations are so powerful, because you've got tons of students coming in and you can easily rank them by GPA, and you can create an arbitrary threshold for GPA. You've still got a big stack of applicants. And now how do you take the next step? You look at their letters of recommendation. 95% will have ones like this. This is a bad one. This is the kind of letter that is one step better than having a return address being a federal prison. Because it's so generic, what it means is that the professor who wrote this doesn't know anything at all about the person, and so just grabbed their generic DocX letter of recommendation and filled it out. So this is what you want to avoid. And yet this is what most people get. If you just hand someone a form and say, hey, quick, write me a letter of recommendation, please, this is probably what you're going to get. And yet it happens a lot, because when you're applying to things, most students spend a lot of time filling out the paperwork, writing their own personal essays, and then the letters of recommendation are almost an afterthought, quick, get 2 and then, or 3, and then be done with it. Let me show you an example of a good letter of recommendation from a lower performing student. This is one that I sanitized, that I wrote from someone who struggled to get his B's. And so you can see it talks about what he's done. It tries to bring out the parts of his personality that would be of particular interest to the graduate school that he's applying to. Here's you don't have to read the whole thing, but here's the thought about how this thing works. If you want a letter of recommendation, sit down, and before you ask anyone to write the letter of recommendation, before you even think about who you'd like to write your letter of recommendation, think about what aspects the place who's evaluating your letter wants. So if you're applying to the SAME military scholarship, leadership is a big one. Whereas if you're applying to a graduate school, leadership probably doesn't matter at all. But there they want people who who have lots of stick-to-itiveness, who don't give up easily. So think about several parts of your personality that the ideal candidate for whatever job, scholarship, graduate school, internship, whatever they want, think about what they want in that candidate. Then think about a professor you'd like to write it, and think about how you've demonstrated those aspects in his class. And I can't tell you how many times I get letters having great ideas about things that they've demonstrated, but for a different professor's class, because people want me to write it rather than the professor that they've actually demonstrated those things to. It doesn't work that way. You gotta, I can't say, I heard that this person did something else in this other person's class. That would be weird. I wouldn't write that. If you find that you're doing a lot of neat things for a particular professor, that's the guy you want to have write your letter. It doesn't have to be a professor either. If you believe that this tenacity, refusal to give up in the face of overwhelming problems was an aspect that's important to get into whatever thing you're applying to, and that you showed really well to your high school football coach, he should definitely be one of the people to write that letter. Maybe not the only one, but you can have it written by someone in the commandant's staff or someone in the athletic team. You can have it written by someone who's involved in your church. You can have it done by someone in a community. In general, if you're applying to a school, at least one letter should be from a professor, but think laterally like that. So then give the person a set of times that you've shown this particular characteristic, and make sure that all those times were things that he would have observed. I got a great one time from bullets from someone who said that he was never gave up in the face of adversity. His mother had died when he was young. His father worked long hours, and he actually raised, even when he was 12 years old, he raised his 5-year-old brother and cooked him dinner and set him off to school, made his lunches. It was a great story. Didn't belong from me though, because I wasn't there. That's the kind of thing that belongs in your personal essay and makes it really strong. So make sure that give the guy, whoever it is that you're writing the letter of recommendation for, give us 2 or 3 aspects that you want us to bring out in your personality. Give us a bunch of bullet points that will remind us of when you've demonstrated that in our classroom, or even better, out of the classroom, and then let us take it from there. Okay, questions on that? Cool. Back to the whiteboard. So here's a problem. And it sounds like a very academic problem. This turns out to be a really real-world problem. You have a system, and the system is a black box. It might be a black box because it's too complicated for you to analyze using first principles. It might be because it's something that someone else built. It might be something that occurs in nature and that you don't understand what goes on inside. But you can stimulate it with an input, and you can measure an output. And so the question is, you want to fully characterize the system. And by fully characterizing means you want to be able to determine the output. For any input, given any input at all. So how can you do this in practice? You've got this black box. We're thinking of it as a circuit, but it could be something mechanical or biological or phenomenological. It could be something involving a society or a government, even like taxation rate versus GNP out. How do you determine the output for any input? So one simple way is to provide all possible inputs. Of course, there's an infinity of those. And we're not talking about a single number. We're talking about a waveform, right? We're talking about this is one input. This is another input. This is a third kind of input. So think of all the possible inputs, all infinity, catalog all the responses. How can you do better than that? Anyone? Can you think of any better way so that you don't have to use every possible input to find every possible, and then find every possible output, so that for an arbitrary input that I give you, maybe one that you haven't measured, you can figure out what its output will be?
Would you model the system?
So that would be a wonderful thing, to break open that black box and see what the circuit is inside it. Let me give an example why I'm saying it's got to be a black box. Back when I was a senior at West Point, they came out with a new type of anti-air defense gun, and it was a monster. It had the longest barrel that I have ever seen, because the longer the barrel, the longer that your round accelerates, and so the longer reach it has. It was called the Sergeant York, and it was already at 4 times over its budget when it was released. And it went on the field to show its training, to show the generals how it actually performed in practice. And it was an abysmal failure. It had the reach. It had a longer, the reach was classified, but it had a longer reach than any other anti-air self-propelled, self-tracked vehicle that I've ever seen. But it couldn't hit anything. And so it was pretty bad because it was so over budget. So the question was why, and it turned out that the problem was with the barrel acquiring the target. So because the barrel was so huge, it actually moved back and forth. And so as the radar system acquired a target, slew the barrel over, it would stop suddenly and the barrel would shake slightly. And because it had such a huge range, a fraction of a degree at the output caused a movement at the end of several hundred yards, and the projectile didn't work. So it wasn't me, but I knew someone who was dispatched to work on fixing that case. And the first thing that she did is say, I don't understand how all the mechanics work, and I'm really not even capable as an electrical engineer of figuring out a differential model that could figure out how the gun barrel moves around. She was a smart cookie. It turns out no one could have derived that model. It would have taken years and years and years. So instead, she just said, I'm going to approach it phenomenologically. I'm going to figure out what kind, treating it as a black box, I'm going to figure out what kind of input causes what kind of output. And that's this problem. So so this is a problem where you don't have access to the underlying model. Another example of when you would encounter would be in a biological system that you want to model how something works, or in there are many reasons why you can't figure out what the underlying model is. So how do you do it from a practical field perspective?
Would you collect several data points and then create a regression model?
Yes, but remember we're working in 2D, not 1D. So it's not that we put in 5 and get out 6 and 3 and put out 2, and then you can sort of map inputs to outputs and then create a regression model. Maybe it's not perfect. It's not that. Instead, what it is that you are putting in entire waveforms, and every waveform that you put in gives you out a different waveform. Maybe this first waveform gives out this, and the second, the sinusoid, brings out this, and this third one gives out something like this. So it's not as simple as just plotting 1D point to 1D point in a 2D space. You've got now a 2D set of points to a 2D set of points. I guess you could somehow create a hypersurface to relate those in 4-dimensional space, 2 dimensions in, 2 dimensions out, but I'm not sure how you'd cover that hyperspace. I mean, the only way to cover it would be with an infinity number of points. Whereas here you can just count the number of points, right? Whereas in 2 dimensions, how the number of possible inputs would range close to infinity. Any other thoughts?
Would you try to just concern yourself with a fraction of the entire picture? So maybe just look at it from a specific time frame?
Tell me about that.
Well, you obviously can't analyze infinity because that's redundant. It's not going to tell you anything. So instead of trying to figure out every single possible output and input, you look at it only from a specific time frame, from like 0 to 5 seconds, and try to analyze a trend.
Well, that you could do that, but let's say all these are between 0 and 5 seconds. We still have the same problem. You've cut down from 0 to infinity to 0 from 5, but we still have an infinity number of waveforms that could exist in that 0 to 5. So that gave us these 3 outputs between 0 and 5. But now my question is, okay, given this data, what does the system do to the square wave? So the problem continues. And it's not an easy problem. What I wanted you to do is just wrap your head about how impossible this problem appears to be. And when I tell you that the solution is you can do it with a single input. Knowing what your linear system does to a single input, one very special type of single input, can tell you what it does to any possible input over any possible time period seems just mind-blowing. But there is a single input that will let you do it. And it's just hitting it with a hammer. It's the unit sample. So if you put a unit sample into your system, what you get out by definition is the impulse response. That is our first objective. And let me tell you in a very hand-waving way why this works. And by the way, if that just seems incredible to you, it seemed surprising to the first people who developed the theory. And electrical engineering is filled with stories about people who develop neat theories like this, and no one believes that it's possible. This is why it works. Here's our impulse. And we put it into our system. So far, I'm just defining what I just said up above. And we get some sort of output. So by definition, you put an impulse in. What you will get out is your impulse response. We'll give it a special letter, a special name, H of t. We'll always call it H of t. And let's say, now if this impulse began at 0, has an area of 1, it would be really surprising if your system responded before the impulse hit. That would be ESP territory. So we know it's going to start off with, it's going to be 0 before 0. And then I'm going to just take a somewhat arbitrary shape of an impulse response. So this is not an impulse. This is the response of your system to an impulse. I meant to draw it straight up at the vertical axis. So you hit it with a hammer, and it rises to a particular value, and then it exponentially decays away. So how does that tell you what your system will do to this square wave or this sinusoid or anything else? All right. I'm going to now give you an arbitrary input. Doesn't even have to start at 0. It could be anything. And we put this into your system. As we take a look at what this thing is, let's pretend we can cut it into samples. We know that the sample is truly infinitely high, and our x of t is not infinitely high. In fact, our x of t here, I'm going to call, to make the numbers easy, 1. And our x of t here, I'm going to call 1/2. And our x of t here, I'm going to call 2. But if we create these impulses, if we model them with impulses going in that have an area of 1/2 or 2 or 1, I think you can see that if I smear this out in time, that this impulse, remember this impulse is like a really tall, very skinny thing that has an area of 1/2 of 1 here. If I smear it out, it will sort of fill in this area. And since this thing has a very tall, skinny thing with an area of 1/2, if I smeared it out by 1, it would have a height of 1/2 over this region of 0 to 1. And the same thing for this. This first impulse, if it's a linear system, would create our H of t that looks like this. And in particular, this H of t would be our H of t pushed back by 1, since this impulse occurred at -1. And we're going to scale it by 1, since its height is 1. And then, if it had a single impulse, I'm going to redraw it in green. here, that would be like having another impulse response shorter here. And that'd only be a 1/2 height because our x of t was only 1/2 there, h of t. And then our next one, you can see where this is going. Our next one over here in, say, orange would look like 2h of t minus 1. Oh, I should have said the first one was plus 1 since it was time advanced. And now what you can do is take the limit of pushing in more and more of these impulses here. You'll take the limit of pushing in more and more of these impulse responses here and add them all up. And so in math, if we smudge the input, then that means we could smudge the output, and then our input will look just like our original x of t, and our output will look like something like maybe like this. And you can do that trick for any input at all. So let's just change that into a math equation. Our y of t, our output, is going to be just equal to, when we talk about the limit as it goes to infinity, that's going to be our, we're going to just integrate all these guys out. And you can see this is h of t plus 1, h of t minus 1. So this is going to be h of t minus, we have to have something that sweeps, right? It's going to be, here it's h of t plus 1, here it's h of t, here it's h of t minus 1. So we're going to say h of t minus tau, and we'll sweep that tau. So when our tau is negative, this will be h of t plus 1, say, and when our tau gets to be bigger, like 1, this will be h of t minus 1. And we're going to then scale it by whatever our original x of t was at those locations. So this is how we can find the output given any input if we know the system's impulse response without knowing anything at all about the system. This is such a common operation, we're going to give it a name and its own symbol. We're going to say it's called the convolution of our input with our impulse response. And this is one you should definitely have in your cards. So we say the input x of t is convolved with h of t. This is the integral to figure it out. By the way, a couple of other mathematical things. Convolution it's commutative. If you've got a particularly heinous h of t, maybe it'd be easier to work with shifting and sliding your x around. So all these things are the same. Questions about that? This is not intuition, and I actually haven't even given you the math example. I'm just giving you a intuitive understanding about what convolution does.
Wait, so really quick, inside the equation, the h of t minus, what is that?
Tau.
Okay.
So we need to come up with a dummy variable, and we typically use tau for a dummy variable representing t. And when you integrate with respect to tau, your taus drop out, and you end up with just a function of t. So big picture, just before I give you the math explanation, up until now, if you have an x of t and it goes into your system, I'll demonstrate the system by h of little t. If you want to find the output, the way we would do it is by taking its Laplace transform, finding the Laplace transform of our system, multiplying them together to find the output, which you can only do in the frequency domain. You can't multiply x of t times h of t does not equal y of t. And then you inverse Laplace transform. But now we found a way that you can do it directly. You can do it directly by just convolving x of t and h of t.